So let's discuss about some flow visualization techniques or the parameters which are used for flow visualization. So let's talk about streamlines. Okay, first. Okay, so what is the streamlines? So first about the streamlines. A streamline basically is a curve that is everywhere tangent to the instantaneous local velocity vector. So a streamline is a curve that is tangent everywhere to the local velocity vector, instantaneous local velocity vector. So this basically is a useful indicator of your flow pattern, a useful indicator of your direction of flow. So your flow is taking place like this, and so let's say at any point, let's say flow is taking place at the velocity is like this. Okay, so you draw a curve which is tangent to the velocity vector at all the points, you get the stream, and that is nothing but a particle. If it is moving along this curve, the velocity, so it's a curvilinear motion by the particle. The velocity is always tangent to the curve tracked by the particle. So these are all streamlines. Okay, so one basic equation you can say that if I write this as dy, this as dx, the velocity vector is like this v. So this is dx, this is dy, the velocity vector is like this. That also has a component vx, which is u, and velocity has a component vy, which is v. So the tan theta I can write dy by dx, and I can write v by u, that is the velocity component in the vertical direction by velocity component in the, because this happens because it's a tangent to the curve. So in the 3D, if you have the three equations, you can write u by dx is v by dy as, I mean, for a 3D is will be w by dz. So this is basically the equation of how this is how your streamline should satisfy. So equation of a streamline. Okay. Okay, now what is path line? The path line is basically the actual path traveled by the fluid particle over some period. Actual path traveled by the fluid particle over some period. Okay, so this is mostly on the Lagrangian concept. And the streak line, the next is streak line. So streak line is basically the locus of fluid particles that have passed sequentially through a prescribed point in flow. What you do is you have a point, you select a point, and now you track all the fluid particles that have passed sequentially. So let's say particle 1 has passed, so you track that. Particle 2 has passed, you track it. Particle 3 has passed, you track it. So it's locus of fluid particles that have passed sequentially through a prescribed. So one particle, say particle is, all the particles are moving in this way. So particle 1 will be here, then particle 1 will go here, particle 2 will come here. So you're tracking all that sequentially through a prescribed point in the flow. So the path line and the streak lines are the flow. So these two, path line and the streak lines, are the flow patterns that involve some time history, that are associated with time history. Whereas streamlines is basically the instantaneous flow pattern. So streamline will give you the instantaneous flow pattern. So mostly these three are used, but mostly, I mean, apart from the other two, you have the streamlines which are mostly used. Okay, let's see some fluid deformation, how it is measured and stuff like that based on the velocity. Based on the velocity components. So this is only kinematics, so we'll be just worrying about the velocity, position and acceleration. So so fluid components, so we define the linear strain rate. Okay, so you have a fluid particle and let's say it has stretched in its direction. So then this is the initial length and it has stretched its direction. So obviously it has traveled dx. Okay, so that dx by the original length. So original length is, let's say, okay, so this is an extra increase in length. Okay, now what we are doing in linear strain rate is we are measuring how much it is getting strained, the rate at which it is getting strained in the x direction, and that is given by dou u by dou x. So the velocity component that matters in stretching along the axis dou is the u. So that is the thing. So this is your linear strain rate, which I write it in this way. Similarly, the linear strain rate in y is dou v by dou y. The linear strain rate in z is dou w by dou z. U, v, w are components of velocity vector in x, y, z. Okay, so these are your linear strain rates, measure of how much it is stretching along the linear direction. Okay, now volumetric strain rate. If I take a fluid and then, so this, if I take a fluid and then, so this is length, this is breadth and this is thickness. So if I put lbt and if I find out the change in volume per unit volume, that comes out to change in length per unit length, change in width plus unit width, change in thickness per unit thickness. So volumetric strain rate becomes basically sum of the linear strain rates. So that is dou u by dou x plus dou v by dou y plus dou w by dou z. This thing is also can be written in terms of vector calculus, divergence of velocity vector, that is dou by dou x of I plus dou by dou y of j plus dou by dou z of k, dot product of this with the velocity vector ui plus vj plus wk. So if you take a dot product you get back the same thing. So this is basically the volumetric strain rate is divergence of the velocity vector. Okay, now if the flow is incompressible, now this is an important statement. If the flow is incompressible, that means you can't change the volume. That means the volumetric strain rate is zero. That means your divergence of the velocity vector is zero. Or the other way of saying it is dou u by dou x plus dou v by dou y plus dou w by dou z is zero for the flow to be incompressible. So you know the velocity components, you can just identify whether the flow is incompressible or not based on this. Okay, so this is one important strain rate, the linear strain rates. The second is your rotational rate. So there are two things, shear strain rate and angular rotation rate. So there are two parameters, we'll see one by one. Okay, so how do we define the shear strain rate? Well, the shear strain rates, that is strain rate in xy, is defined as half of your, so this is how it deforms. Okay, so half of dou u by dou y plus dou v by dou x is your shear strain rate in xy. So in the plane xy, how much it is shearing. And similarly you have yz, which is half of tau v by tau z plus tau w by tau y, and similarly you have the shear strain rate in zx, which is half of tau w by tau x plus tau u by tau z. So these are the shear strain rate, which measures how much the shape change is happening, the rate at which the shape changes are happening. Okay, so now in order to define the rotation rate, we come back to another important parameter called the curl of V. Okay, so the curl of V is basically defined as, basically this curl V represents the rotation rate at which the fluid particle is rotating. Okay, so how do I define curl of V? Curl of V is defined as ijk. The curl is tau by tau h, tau by tau y, tau by tau z, and the velocity components u, v, w. So if you find out this vector, what you get is the three components of this. Okay, so those are going to be like this: I into tau w by tau y minus tau v by tau z. So I into the cross product minus plus j, so that I have just taken inside tau u by tau z minus tau w by tau x plus k into tau v by tau x minus tau u by tau y. So these are the rotation rates in x, y, z. Okay, so when you say the flow is irrotational, we mean that curl v bar is 0. Okay, that is the check for irrotation. The curl v bar is not equal to 0, we mean the flow is rotational. So that is it. So there is another, we define this rotation vector as well. Rotation vector omega bar is half of curl. So it's basically the same quantity but just defined as half of curl v. So that is how you define the rotation vector. Okay, and that also has to be 0 for irrotational flow. So you have three things here. One is, so let's combine whatever we have studied. Pure translation. So when is pure translation possible? So you have a fluid, it's just getting translated in this without any shape changes or any stretching in x and y. So this happens when the horizontal velocity is constant, it's not varying with x. Vertical velocity is constant, it's not varying with that. So that is pure translation. And then you can have linear deformation when you have u varying with respect to x. So if this is the thing, it may just stretch out. Okay, that means u is a function of x, so that it may happen linear deformation. So you have fluid motion, which can be pure translation. You can have linear deformation depending on the velocity vector, and then you can have your u and v in such a way that the particle can just shape change can happen, a shape change like this. So that is your angular deformation, which depends on your shear strain rates, which we have discussed. And then you can have pure rotation. So particle like this, which just rotates in this way, pure rotation. So that is possible only when your curl is not 0. Okay, so these are the various fluid motions, and we have seen the methods which so basically two things are important here: incompressible and rotational things. So incompressible when your divergence is 0, rotational when your irrotational when your curl v is 0. And we have seen the various kind of fluid motions.